In today's video, we're going to calculate the pH of a weak acid buffer with a small addition of a strong base. In this case, we're going to use a 50-50 mixture of acetic acid and its conjugate base, acetate ion, in the form of sodium acetate. The moles of acid and base are equal. That's an important statement for you to remember if you're looking at this as a question on a test. Because if we look at the we're going to do the Henderson Hasselbalch equation, which says, let's try to get this down here and get this over here so we can see what's what. And the Henderson Hasselbalch equation says pH is equal to the pKa plus the log of the base over the acid. All right. And so this ratio is very important because we're going to have a beginning and an end. Okay. And what we have is the acid, which is going to be down here, and the conjugate base is going to be here, and we're going to add, okay, OH ion in the form of sodium hydroxide. And I'm going to explain to you what's going on here. So we're going to keep playing with this equation here. The pKa is the negative log of the Ka. So it's a textbook value, and the pKa for acetic acid, pH, is equal to 4.74. Some might say 4.75. That's close enough for now. And it's going to be plus the log of the base over the acid. Now this ratio is pretty darn important. Okay, so if we think of if these are equal, if the acid and the conjugate base are equal, and they are because it says so, all right, this becomes the log of 1, and the log of 1 is equal to 0. So this whole thing drops out, and the pH equals the pKa. So, that would be our starting factor. So if we had two vials or two beakers, each one had 5 milliliters of 0.01 molar, which is what we've got. All right. These are givens in the problem. We have 5 mils of 0.01 molar acetic acid. All right. What we're going to do is we're going to convert everything to moles of acetic acid and acetate ion and OH. So if we look at volume times concentration, that's in volume times concentration. Concentration could be molarity. Okay, this could be liters times moles per liter. And the liters cancel out, and that leaves us with moles. So we'll use this. We're going to use this little equation right here to calculate all of our moles with. All right. So the first thing we want to calculate is the moles of acid. Well, here, these are the givens. The acetic acid, we have 5 mLs of 0.01 molar. So 5 mLs, okay, is 5 milliliters, which is going to be 0.005 liters. So that's our volume, times our concentration, which is 0.01. And if we do that math, we're going to get 5 times 10 to the minus fifth, and that's going to be moles of our acetic acid, right? And we know that it's also going to be the same concentration and the same number of liters or milliliters for the conjugate base, all right? So these 5 mils of acetate ion of 0.01. So this is moles of A, and it's also equal to 5 times 10 to the minus 5 moles of B, which is the conjugate base. So now we rewrite the equation now. What do we have? We have pH equals pKa plus the log of the base over the acid. But we know the base of the acid. We know these are starting numbers now. All right. If these were equal, this would be the log and a log of 0. Okay, log of 1 is equal to 0, so the pH would be equal to pKa. pKa, by the way, is the negative log of the Ka. All right, and these are textbook values. You can look them up in a book. They'll probably give you a cheat sheet, or they give you the number in the question and the problem, because they want to test your understanding of how buffers work. All right. So the pKa in our case is 4.74 for acetic acid. So we'd say pH is equal to 4.74 plus the log. Okay, now instead of saying B over A, we're going to use this number. We're going to say 5 times 10 to the minus 5 over 5 times 10 to the minus 5. All right, now this is the base, okay, and this is the acid, all right? But now we're going to add 1 milliliter of OH ion, which is a really strong base, all right? And they give us the concentration. It's 1 mil of 0.01, all right? So the moles of OH, okay, is equal to 1 milliliter. If we got to convert that to liters, so it's going to be 0.001. Okay, that's 1 milliliter times the concentration is 0.01. So if we do that math, we're going to have 1 times 10 to the minus 5 moles of OH. Now, where do we put this moles of OH? Okay, well, if we add 1 mole of OH to this system, okay, so we've got a beaker full of here's our beaker. Okay, let's call this our beaker here. And what we've got now is 10 mils. Okay, but the number of moles of acid and conjugate base are the same. So we would say that this now is 10 ml, but we don't care about that. But it also, we're going to have 5 times 10 to the minus 5 moles of conjugate base plus 5 times 10 to the minus 5 moles of acid. That's the acetic acid, right? So now we have this pH equals this times this. So now we're gonna, this strong base is going to react with this acid. Let me do it off to the side here. If I took some acetic acid, CH3COOH, and I add some OH minus to it, I'm going to play something called lasso chemistry here. I'm going to lasso this. Okay, what do I have in here? I have water. Okay, so if I bring this out, I'm going to have CH3COO minus plus H2O. Right? We don't care about H2O. It's going to have no effect on our pH. We don't care about the sodium either. The sodium has no effect on pH. But what did we do? We took away one of our acids and we created another base. So this amount of OH, where did our OH go here? 1 times 10 to the minus 5 OH gets added to our base, okay, which is right here. So we're going to say plus 1 times 10 to the minus 5. Now we have that much more conjugate base, all right? That's this guy. And we have one less acid. So this is going to be, it's by the same amount, minus 1 times 10 to the minus 5, all right? Now let's take a look at this here. So this is 5 times 10 to the minus 5 plus 1. That's equal to 6 times 10 to the minus 5. And this is 5 minus 1, which is going to be 4 times 10 to the minus 5. And these can cancel out, and this is equal to 1.5. All right? So now let's take a look at let's take a look at this whole thing right here. Let's take a look at that whole thing right there. All right? So now what do we have? We have the pH is equal to 4.74 plus the log of 1.5. Now if I get my handy dandy calculator out, the log of 1.5 is the log of 1.5 is equal to 0.176. Okay, so this is we're gonna say the pH is equal to 4.74 plus 0.176, which is equal to, I call it 4.92. All right. So this is our final answer. Okay. So very predictably, by adding a strong base to a weak acid, the pH should go up, and it did. It went from 4.74 to 4.92. It went up. But, and there's a big but here, it didn't go up very much. These numbers are so close to each other they might even be considered noise. There's not a whole lot of difference between these two because they're at the low end of the pH scale. You know, it's just we predicted it would go up, but not this little. It hardly went up very much at all. It stayed real close to its original number. When all of the acid is exhausted by the OH, then the pH will, like a rocket, shoot off to the moon. It'll go up to 10, 11, 12, and higher, and it'll go up very steeply. Okay, even adding 1 mil to this little amount of stuff. So, but by turning it into a buffer, okay, by mixing it with the base and the conjugate base, or the big conjugate base and the acid of the weak acid, we created this buffer, and so that's your final answer. Um, and what I'm going to do here is I'm going to leave these here. You can read them on your leisure. Press the pause button on the video. Carefully read everything in here. It'll all make sense to you now. These are the calculations that you're going to need. Not very many. I actually put a little more than I had to, but I'm trying to teach you something here. And so I hope you enjoyed the video. I'll see you guys on the next trip. Thanks. This is Bill.